Hello everyone. In this lecture we will discuss about semi-batch reactor with second order reaction. So the production of methyl bromide is an irreversible liquid phase reaction that follow elementary rate law. This is the bromocyanide reacted with methylamine. It will give us methyl bromide and cyanamide. So in this reaction, in semi-batch reactor, uh, this component A, which is bromocyanide, reacted with methylamine, and it will give us methyl bromide and cyanamide. So the component A is bromocyanide is component A, methylamine is component B, methyl bromide is component C, and cyanamide is component D. This reaction is carried out isothermally. The temperature in this semi-batch reactor is constant, and the aqueous solution of methylamine is the concentration of methylamine is 0.025 mole per dm cube. Methylamine, which is component B, it is added to the component A, which is the bromocyanide. So the volumetric flow rate of methylamine, which is component B, the volumetric flow rate of component B is 0.05 dm cube per second. The initial volume of component A in the semi-batch reactor is 5 dm cube. So V naught, which is the initial volume of the reactor, is 5 dm cube with bromocyanide concentration 0.05 mole per dm cube. So Ca naught, which is present in the semi-batch reactor, is 0.05. Initial concentration of component A in the semi-batch reactor is 0.05 mole per dm cube. But after adding component B to the component A, the concentration of component B will decreases with the passage of time. So the specific rate constant of this reaction is 2.2 dm cube per second and 2 mole. The question is solve for the concentration of component A, component B, component C, and component D. And rate of reaction is a function of time, and analyze your result. So we will solve the we will draw the concentration of component A, component B, component C, and component D in the semi-batch reactor with the passage of time. So the first step to solve this type of question is write the mole balance. So this is the symbolic form of the above reaction is A plus B give us C plus D. The mole balance on component A will give us Ca divided by dt is equal to Ra minus V naught into Ca by V. Similarly, the mole balance on component B will give us this equation. Mole balance on component C will give us this equation. Mole balance on component D will give us this equation. Now the second step is the rate law. The elementary rate law for this reaction is Ra minus Ra is equal to Kca and to Cb, where Ca and Cb are the concentration of component A and component B, and K is the rate constant. Its value is 2.2, which is given to us. The relative rate for this reaction is minus Ra equal to minus Rb is equal to Rc is equal to Rd. So this is the relative rate law. Now combine the mole balance with the relative rate and rate law. We will give us this type of we will give us these equation for component A, component B, component C, and component D, because in place of Ra we will write minus K into Ca into Cb, because minus Ra is equal to K into Ca into Cb. So we will get this type of after combining the step 1, step 2, and step 3. After combining mole balance, relative rate, and rate law, we will get these 4 type of equation. Now from stoichiometry we can get the conversion of A, which is Na naught is the initial mole of A in the reactor, and Na is the mole of component A at any time in the reactor, and this is the initial mole of component A in the reactor. Now after stoichiometry, and this V is equal to V naught into time. This is the volume of reactor at any time. So with the passage of time, the volume of reactor will increases, because with the passage of time B is entering to the semi batch reactor. Now evaluate evaluate the problem in the ODE solver, which is Polymath in this case. So when time is equal to 0, when time is equal to 0, the concentration of A was 0.05, which was present in the same batch reactor. When time was 0, there was no B, no C, and no D in the same batch reactor. So when time was 0, there was no component B in the reactor, there was no component C in the reactor, and there was no component D in the reactor. But when time was 0, the initial volume of the reactor was 5 dm cube. So the volume of reactor is increases with the passage of time, because B is entering to the reactor with the passage of time. So this is the Polymath result, and this is the concentration versus time graph. Concentration versus time graph. The time was 0 initial and it is 500. We assume that the final time is 500. So the concentration of A, B, C, and concentration of component D. So similarly, this is the relation between time and the relation between time and minus RA, or the relation between time and plus RA will be like this type. It will be like this type. It will be like it will be inverted. So it will be it will be like this type. Will be like this type. For plus RA, the relation will be like that type. So if you write plus RA or minus RA, you can easily determine that with the initial the rate is increases, and the rate increasing will be from this side to this side. So if you are using plus RA with the passage of time. Now come to the Polymath. We will plot the result. So open Polymath Professional, click on it. It will take some time. It will take some time to open the Polymath, so it will take some time. So this is the Polymath 6.10, and these are the program, file, window, and help. Click on program, linear equation, non-linear, differential, and regression. So we are solving the differential equation. Click on it. This interface will open. Now enter a new differential equation. If you click on it, it will show us enter new differential equation, and this is new explicit equation. So click on it. So this is the enter differential equation. The first differential equation is dCA CA divided by dt is equal to RA minus V naught multiply by CA divided by volume of reactor at any time. So this is the initial value. The initial value of component A, which was present in the reactor, was 0.05 mole per dm cube. So 0.05. So click on. You can write comments, but I am leaving it. Click on done. So the first differential equation. Now click on it. Enter the second differential equation. The second differential equation is dCB by dt. dCB by dt is equal to RB plus V naught into VB naught minus CB naught minus CB divided by volume of the reactor. But from relative rate, we can say that minus RA is equal to minus RB. So in place of minus RB, we will write minus RA, and when minus sign cancel with each other, then RB will equal to RA. So in place of RB, I am writing RA plus plus RA plus V naught into CB naught minus CB divided by volume of reactor at any time. So initially there was no B present in the semi-batch reactor. Initially there was only and only component A in the semi-batch reactor. So CB naught was 0. Click on done. Enter the third differential equation, dCc divided by dt. The third differential equation is dc by dt is equal to rc minus v naught into cc divided by v. So in place of rc we can write minus ra, because from relative rate we know that minus ra is equal to minus rv is equal to rc is equal to rd. So in place of rc I am writing minus ra, so minus ra minus v naught into Cc divided by volume of reactor at any time. Initially there was no component C in the reactor, so it was 0. Click on done. Now enter the fourth differential equation for component D. So dCd divided by dt. The fourth differential equation is dCd by dt is equal to rd minus v naught into cd divided by v. So from relative rate we know that rd is equal to minus ra. So minus ra into minus v naught into the concentration of component D divided by volume of reactor at any time. Initially there was no component D, so it was 0. Click on done. And this is the fourth equation. Now undefined variable are v naught, v, cb naught and ra. Now this v naught is the volumetric flow rate of the entering component B. So the volumetric flow rate of the entering component B was v naught was, it is given in the problem that the volumetric flow rate of component B which is entering to the semi-batch reactor is 0.05 dm cube per second. So 0.05 dm cube per second, but don't write the unit of volumetric flow rate or concentration or volume or time in this interface. So now the undefined variable is RA, V into CB naught. This CB naught is the concentration of component B which is entering to the semi-batch reactor. This is the concentration of component B which is entering to the semi-batch reactor. So it is given that the concentration of component B which is entering to the semi-batch reactor is 0.025 and the volumetric flow rate of component B which is entering to semi-batch reactor is 0.05 dm cube per second. So CB naught is equal to 0.025 mole per dm cube. So now undefined rate of component A and volume. So volume we can V naught, the relation between volume and time, this is V naught so this is plus sign, sorry. So this is the we will this V can be obtained from the relation between volume of reactor and time. So V is equal to V naught and to volumetric flow rate of component, and this is the time. So this is the volumetric flow rate of component B which is entering to the reactor at the initial time, or this is the volumetric flow rate of component B which is entering to the reactor, and this is the time. So when time passes the volume of reactor will increase. So it is given, or you can derive it from the differential equation between dV by dt and time. So this is the now this is V naught is undefined. V naught is given to us, initial volume of reactor is given to us, it is 5 dm cube, 5 dm cube. Now Ra is unknown to us, so Ra can be obtained from the Rate law. Ra is equal to minus K into Ca into Cb, Ca into Cb. Remember, we are writing these differential equation in term of rate of component A. So we there was Rd, but Rd from the relative rate was equal to minus Ra. Similarly, Rc was equal to minus Ra and Rb was equal to Ra, and this was already given. So remember this Ra, right? We will write the equation in term of only component A or Ra, in term of Ra, not in term of Rb, Rc or Rd. So these are the relative rate simplify our work. Now this is the undefined K. K is the rate constant or reaction rate constant. The value of rate constant for this isothermal reaction was given 2.2. It was given to us 2.2 dm cube per mole into second. So undefined K value. So now enter the initial and final value. Initial and final value of the independent variable. So remember, the independent variable in this semi-batch reactor is time. So with the passage of time, concentration and rate changes in the semi-batch reactor. So when time passes, concentration changes and rate changes. So the time is independent variable. So this is the initial and final value of the input variable. Input variable is time. So click on this one. Enter the initial value. The initial time was 0. Enter the final value. So the final time to full the reactor from component B can be obtained from the space time, and the space time is nothing but volume of the reactor divided by volumetric flow rate. So volume of the reactor is the volume is filled up to 5 dm cube, but volumetric flow rate is 0.05. so you can assume a 10 dm cube, and this one is 0.05. so divide 5 divided so assume there is 10 and this is 0.05. so 10 divided by 0.05, you can obtain the space time. So I'm similarly it will take some time to open and close the valve of semi-batch reactor when the volume of reactor become full. So it will take at least 4 or 5 minutes to full the it will take at least 1 minute to full the volume of reactor from 5 dm cube to final volume of the reactor. And similarly, it will take about 4 or 5 minutes to afraid the valves of the semi-batch reactor to open or close. When the reactor become full from component B, then we will close the valve that not overflow the reactor. So I am assume 5 minutes, and 5 minutes is equal to about 300, but 6-7 minutes will be equal to 500 seconds. So I'm assume 500 seconds the total time when the volume of reactor become fully full. So it will take about 500 seconds. So I'm taking 500 seconds. Now this is the this is ready for solution. So I'm drawing table. You can also plot graph. Click on it. This is the report. So this is the click now solve. This is the solve button, the purple. So you can also export from Excel. So click on the purple button. So I'm clicking on it. It will take some time. You see, it will take some time to plot the graphs and tables and reports. So it will take some time. This is the Polymath report, the value, initial and final value, Ca, Cb naught, and this is the differential equation, for differential equation, and this is the explicit equation, general equation. So these are the report, and you can see the graphs. This is the graph between C and Cb, Cc and Cd. You can drag it and double click on it. So you can change the x-axis and y-axis, this one. So you can also add the grid line, but I am not adding grid line. Similarly, this is the title, you can also the relation between concentration versus time in the semi-batch reactor. So you can also add subtitle, click on it. So this is the graph. Now you can, this is the table and this is the design, click on it, and this is the curve width. You can increase or decrease the curve width, so I am increasing it. And this is the border width, so it is 2, it can be decreased to 1, so it is okay. A draw marker, so this is the also good. Now curve, a title, XY, and font, you can also scale and margin, and I'm closing it now. So you can also this is the curve and function, curves and function. So this is the time, so we can label it, double click on it. The time is in second, so I am writing SE second and click on OK. So time in second will appear. I am closing it. So this is the, now this is the graph between concentration and time in the semi-batch reactor. So if this is the x-axis and this is the y-axis. So on x-axis there is time, on y-axis there is concentration. So this is the concentration of component A, concentration of component B, concentration of component C, concentration of component D. So the concentration of component A is decreasing with the passage of time in the semi-batch reactor, and after 4 or 500 seconds the concentration of component A in the semi-batch reactor is about 0.0 mole per dm cube. So A is fully converted after 500 or 400 seconds in the semi-batch reactor. So the concentration of A is decreases, but the concentration of B is increases with the passage of time, because with the passage of time more and more component B will be entering to the semi-batch reactor, so its concentration is increases with the passage of time. Similarly, the A and B when reacted, it will give C and D. So the concentration of, this is the concentration of component D, and the concentration of component D is equal to the concentration of component C. So with the passage of time the reaction rate changes, A and B converted into B with the passage of time. So the concentration of A decreases with the passage of time, but the concentration of component C and D is increases with the passage of time, because with the passage of time more and more product will be producing in the semi-batch reactor. But if you see from this point after 400 seconds, after 400 seconds, if we further increase component B to the semi-batch reactor, then the concentration of component C and D will be decreases, because when the reaction is completed and we entering a further component B to the reactor, then the component B will diluting our product O. So when the component B diluting our product, then its concentration will increase O, but it will dilute our product. So when our product become diluting, then its concentration will be decreases, definitely its concentration will decreases in the semi-batch reactor. So here you can see the concentration of C and D is decreases. Remember, this line is for component C and component D. So the component C and component D. So this was relation between concentration and time in the semi-batch reactor. You can draw the relation between rate of component A and the time. So unclick it, come to time, independent variable is time, and this is the rate. So this is the rate. Now close it. So you can see I already said that the rate of component, the for plus R A, the rate will be like this one, but for minus RA the rate will be this type. Already discussed it. So the rate of A at at 20 second the rate of A is maximum. So if we increase the rate at this time, suppose the rate of A increases in this direction, in the downward direction, so at 20 second or 30 second the rate of A will be maximum, and after 500 second the rate of A will be go to 0. Suppose the rate of A here is 0. So this was all about the semi-batch reactor. This was all about the semi-batch reactor. Thank you very much for your attention.